Okay, here we are with the second half of Lecture 8, and this time we're going to look at a bunch of examples and one or two other ideas which need to be talked about. One, before we do an example, is the idea of what happens on this graph when you're focused on this point A and you're up on the graph and you're calculating this derivative, this limit of the average rate of change. We already saw that we can calculate that as a limit. We'll see some examples of this in just a minute, but I want to talk geometrically about what we would get. If we think about x as sliding in towards A, we also think about this point as sliding in, but before we do that, we could think of the line that connects those 2 points, the slope of which is the average rate of change. But what would happen to that line as we slide in? Well, in this case, it would change and go like that. And as the point slides in more, it would change again and look like that. The closer this point gets, the lines don't change quite as much. Is there a limiting line? Is there a single line to which all of these other lines seem to approach? And the answer is, in most cases, yes. And those are the nice cases. Those are when we have an actual derivative. And you'll hear this expression a lot, that the derivative is also the slope of something called the tangent line. The tangent line is an interesting concept, a very, very interesting concept. We came across it, you all came across it, of course, when you talk about a circle. That's a circle, mathematically. Anyway, if you take a point on the circle itself, the tangent line would be a line that would go like that. And sometimes you hear that a tangent line is a line that crosses the circle only once. Well, that's not really a good definition, because what if we were only talking about a semicircle? Could you have a tangent line for a semicircle? Well, of course. So would this be a tangent line? It only crosses the circle once. Well, I don't think anybody would really like that being a tangent line. There's something else about tangency that's involved. There's got to be something else, and there is. There's a different notion, not having to do with the fact that it touches the circle only once. No, in fact, what a tangent line is the limit of a bunch of other lines that are not tangent. Like this line cuts through the same point, but it's not tangent. But as you get closer, you see those lines get to approach the tangent line. Now, I mentioned this in one of the earlier videos, that what's happening if you look at it as a mouth, if this is supposedly the tangent line, if that is really the tangent line, then all of these other lines, as this point slides in, all of these other lines should make it look like this. If you think of this as a mouth, the mouth is closing as the point slides in. So you can imagine these lines getting closer and closer to the alleged tangent line, so that in this picture, at this point, the tangent line would look like this. Okay, so it doesn't really have to do with touching the curve only once. As a matter of fact, if you have a curve like this, a tangent line right here will obviously cut through the curve many times. So it's not a matter of cutting the curve once, it's a matter of the tangent line being the limit of other lines that have that same point and cut through the curve. Now there's an interesting thing that happens where a curve looks like this at some point, where it has what you might call a cusp. If you look at this point and you're looking in from this side, the lines that you get will all have slopes that are like this, positive. And if you look from the other side, the lines will all be like this. So you might say that as your point slides in this way, you're getting close to this line. As you're sliding in this way, you're getting close to this line, and they don't come together. And that is the case. When you have a cusp, the point where the cusp occurs, is a place where the derivative will fail to exist. And you can sort of sense why, because the limit from the left and the limit from the right are not all the same thing. Okay, time to look at examples. So let's take our first example, which is our old friend y equals x squared. So f of x equals x squared. And this is our y. And we know what the graph of it looked like. That's not a big deal. But I'm interested in thinking about what happens, let's say, between the point x equals -1 and x equals 2. Now, there's one thing we could do. We could go up to the graph at 2. We could go up to the graph at -1. We could play connect the dots. And what that would be the average rate of change in going from -1 to 2. That would be your delta y over delta x. And you could calculate that. That would be f of 2 minus f of -1 over 2 minus -1. This is not the derivative. This is the average rate of change. But you could calculate this. F of 2 would be 2 squared, so that would be 4. F of -1 would be -1 squared, that would be 1, divided by 2 minus -1, which would be 3. And so this would be 3 over 3, which is 1. And that does look like the slope of this dotted line that I just drew. So that's kind of a reality check. But that's not the question I'm interested in. What I'm interested in is what is the instantaneous rate of change at -1? What is f prime at -1? Graphically, that would have to be the tangent line. That would be a line that would come in like this, right? Now, how are we going to get to that? And the answer is from the definition. That's all we have right now. So the definition tells us that this idea, f prime of -1, is a limit. And now we have a choice. We get to decide whether we want to have x sliding into -1 or whether we want to have an h going to 0. I'm going to choose to have x slide into -1. So the definition of derivative, the derivative of f at 1 is the limit as x approaches -1. Did I say 1? I meant -1 here. The derivative at -1 is the limit as x approaches -1 of f of x minus f of -1 divided by x minus -1. All right, and we just fill in what we know. The limit as x goes to -1 of, what's f of x? Well, I have a formula for it. It's up there in case you forgot. It's our old friend x squared. So f of x is x squared minus f of -1. I think I can calculate f of -1. That'd be -1 squared. -1 squared is 1. Divided by x minus -1. That's x plus 1. Okay, this is a limit problem. We've been doing these for the last few days. A reality check, as x goes to -1, the bottom is going to 0, the top is going to 0, so this is a 0 over 0 situation. That's bad news. But we've done enough of these that I think you know what's coming. We're going to factor the numerator. So it's x minus 1, x plus 1. The x plus 1's cancel, leaving you with the limit as x approaches -1 of x minus 1. And that is easy to calculate because there's no problems. -1 minus -1 minus 2. Does that make any sense? Let's look at the picture. Does this line that's supposedly tangent to the graph of y equals x squared, does that have a slope of -2? It certainly looks like it to me. So yes, this is what we want. This is giving us the derivative, the slope of the tangent line, the instantaneous rate of change, which is -2 at the point -1. Now you may be wondering, maybe not, what would happen at 2? What's the slope of the tangent line here? What's the instantaneous rate of change here? Well, obviously it's going to be steeper. Well, let's do it again. It's not a big deal. So I need this time the derivative at 2. We'll do it the same way. It's the limit as x approaches 2 this time, of f of x minus f of 2 over x minus 2. Fill in limit as x approaches 2 of f of x is x squared, f of 2 is 2 squared, or 4, x minus 2. Do your reality check. As x goes to 2, the bottom goes to 0, top goes to 0. By the way, this is going to happen every time we take a derivative. Every time you take a derivative, the difference quotient, your delta y over delta x, is always going to be a 0 over 0 situation. If it's not, you did something wrong, because as x approaches a, your bottom is going to go to 0, and the top had better go to 0. If it doesn't, this function is just not going to have a derivative. It's going to be kind of like your cusp situation that we talked about a minute ago. Okay, so this is no more difficult than the last thing that we did. We're going to have to factor the top. X minus 2. Whoa, that was weird. X minus 2, x plus 2. And the bottom is still x minus 2. Cancel off the x minus 2's, gives us the limit as x goes to 2 of x plus 2, and that's obviously 4. And so a slope 4 is what we saw in that steep part of the y equals x squared curve, to no one's surprise. Okay, let's do some more examples. We'll do them a different way this time. What about calculating f prime at a, where f of t is 2t plus 1 over t plus 3. Okay, this time we'll use the a formulation, the h formulation, excuse me. So f prime at a. Oh, by the way, in this problem, they didn't tell us what a was. Big deal. We're just going to let it sit. So f prime of a, by definition, would be the limit, as this time it's the h goes to 0 form. Limit as h goes to 0 of f of a plus h minus f of a all over h. And now we fill in. What is that? Limit as h goes to 0. Now we have to know what f of a plus h means. Well, our function here does what to any number? It multiplies it by 2, adds 1, and then divides the number plus 3. So in other words, f of a plus h means 2 times a plus h plus 1 divided by, what I'm plugging in is a plus h plus 3. That's f of a plus h. I've still got to do f of a. That means replace t by a, so that's just going to be 2a plus 1 over a plus 3. And all of that is divided by h. That looks kind of messy and painful, but you just have to grin and bear it sometimes. So let's simplify. Yeah, I'll multiply out everything. I don't like multiplying, but 2a plus 2h plus 1, and that's over a plus h plus 3. I don't think I can do much of anything there. You know, maybe we just got to get our common denominator right away. I don't think that was very helpful, multiplying that out. All right, let's get the common denominator. Because you see what I'm going to do? These are two fractions right in here where I'm subtracting. So I need to get the common denominator of that times that. So the common denominator is a plus h plus 3 times a plus 3. So I need to multiply 2a plus h plus 1, that's this guy, by a plus 3. and then subtract 2a plus 1 times the other denominator, which is a plus h plus 3. And now that's all over the common denominator. And that whole thing, remember h, is still there, still divided by h. So what we have to do now is make this a compound fraction, h over 1, flip and multiply by it. So this is going to give us the limit as h goes to 0 of, and I suppose while I'm at it, I might as well multiply everything out, see what happens. So we get 2a squared plus 6a plus 2ah plus 6h plus a plus 3. That's this part multiplied out. And then I've got to subtract, and be very careful that I subtract everything. Oops, I erased it. I got to subtract everything. So we're going to FOIL that too. So it's 2a times a, 2a squared. And we're going to have minuses everywhere. 2ah, continuing, minus 2a times 3, which is 6a, minus a, 1 times a, minus 1 times h, minus 1 times 3. And that whole thing is divided by a plus h plus 3, a plus 3, h. That came from flipping this and multiplying by it. So the h ends up on the bottom. Now, with any kind of luck, this will simplify and be able to cancel us off an h. So let's see. Here's a 2a squared, and there's a minus 2a squared. That's a good start. Here's a 6a and a minus 6a. That's good. Here's a 2ah, and here's a minus 2ah. I like that. Then what? Here's a plus a and a minus a plus 3 and a minus 3. And what's left? I don't think I can cancel anything more, but there's not much left. Looks like it's just 6h from here, minus h, 6h minus h, I think that's 5h most of the time. That's all that's left. Divided by, well, there's a bunch of stuff downstairs. A plus h plus 3, a plus h, h. Now I'll cancel the h's because I'm multiplying, and we're left with the limit as h goes to 0 of 5 over a plus h plus 3, a plus h. And folks, believe it or not, I can calculate that limit, because as h goes to 0, there's not much bad happening. The 5 stays 5, and the h is gone. I've got a plus 3, and I've got a plus 0. So that is it. That is the derivative. Okay. It turns out that we are going to have a lecture 8C, because I need to pause it right now. So there's much more examples coming. We'll just take a break at this point for a while.